Hey everybody, welcome back. We're talking about grid approximation, and we're starting to get a sneak peek into our next unit, the Markov Chain Monte Carlo, or MCMC, that I have up on the screen. So just a quick reminder about why we need MCMC. For a non-trivial case, like this skew normal distribution, there was a lot of space outside of this sphere, spherical shape, egg shape. Everything roughly outside of what I just circled, we really didn't need computation at any of those points because the posterior is basically impossible. That posterior combination of the parameters given the observed data is virtually impossible. So wouldn't it be great if we can focus on the part of the posterior that is possible and go ahead and stay in that middle bit even more? But we still need, some idea of details. So the way we will do this is we'll use what is called Markov Chain Monte Carlo. And today, I just want to give a preview. We're going to define a lot of things, and I'll show you a lot of things next unit. We're going to have our next synchronous activity on Tuesday. So this is going to be a week from today, next Thursday. We're going to start the next unit. So Markov Chain Monte Carlo will feature basically these, what I call them, workers, or chains, which are sequences of random numbers generated from what we hope is the posterior. Workers or chains that explore the posterior. So these chains, as they're called, again, sequences of numbers generated at random from our posterior density, they're going to have starting values like what you see here. But there will be an algorithm involved that will help us essentially narrow in on the area of the posterior that is most likely. Now, I know that's not exactly how it went. It doesn't go in a spiral like that. But you can see already that our first step is a good one. The first step already takes us from a spot where the posterior is impossible towards a part where the posterior is highly, highly likely. And then the second step doesn't take us back out. The next steps stay inside of our posterior. So this is the posterior with two variables, but it would work the same in our three-dimensional case. So I did say workers or chains. The thing is that it's not sufficient for us to have just one of these chains because we don't want to leave anything up to chance alone, that is. So we're going to start another chain at another random spot. That's not a random spot. I just wanted to put it on the other side of the space there. And maybe this one takes 2 steps to get there. And then I'm going to have a third chain. I'm going to start at a random spot. Of course, just by chance, you could have started it on the posterior. But for now, let's pretend that you don't. All right, and it takes a few steps to get there. Eventually, the algorithm will ensure that you're actually covering the same space. MCMC will ensure, to the best of its ability, that we are sampling at random from the posterior. So we need to come up with some diagnostic measures about how many samples to take until we have a pretty good idea of what that posterior looks like. If you remember in our activity, we were approximating an integral using random samples from a beta. And we showed that with 100,000 random samples from a beta 3 1.5, we got a really good approximation of that distribution. With 10 samples, or even 100 samples, you wouldn't have as good an approximation. So we need to come up with some kind of diagnostic measures that tell us when we have taken enough of these MCMC samples. So I thought as we're moving into MCMC, it's probably useful to take a look at and contrast MCMC versus grid approximation. So grid approximation is not general. It's not used because it's not general. It depends on the grid too much. Like the resolution at which, for example, you can observe the posterior depends on the grid that you specify. So you do, in a way, have to tune the grid. MCMC is general, and there is no grid. But you do still have to tune something. You have to tune the sampler itself. Remember that we're generating random numbers from what we hope is the posterior. So how you generate these random numbers, how you move about the space, how you generate random coordinates to move about the space has to be tuned. We'll talk more about it. So we have to tune the sampler. So with grid approximation, we do obtain the full posterior because we evaluate it at every single possible data point. And if we're able to, every possible grid point. And if we are able to evaluate it at every possible grid point, we obtain the true full posterior. With MCMC, we sample at random and then eventually, I guess I'm still having problems with my stylus and I don't know why, converge, there's the key word, to a stationary distribution. So stationary distribution, I mentioned this briefly last time, is one where the mean and the variance are constant. And this distribution, once we take enough samples from this stationary distribution that our workers have converged into, we take that to be our true posterior. So if that sounds like you're sort of grasping in the dark, that's kind of what you're doing. But the grasping has a method. The grasping leads you to areas of higher posterior density and away from areas where the posterior is essentially impossible. The issue with grid approximation, of course, is it takes forever. To evaluate it at enough grid points at any non-trivial case. Takes forever for any non-trivial case. So the first thing we're going to look at is how can we tell that our workers that are grasping in the dark for the posterior distribution, how can we tell that they have converged to a stationary distribution? That's our first task. So we're in R for this. So remember that before I took a sample of points and I summarized them using the posterior mean, median, credible interval. Now I'm going to pretend that I have samples from 3 separate chains. I'm trying to mimic what would happen in an MCMC sense with my grid approximation. I'm going to pretend like I have 3 chains, and I'm going to have each chain give me a separate random sample of 5,000 samples. A separate random sample where the probability that a particular combination of parameters makes it into my sample is equal to the posterior probability, and I'm sampling with replacement. So set the C to make sure I get the same thing every time, right? And altogether, I get 5,000 times 3, 15,000 samples that I hope are all samples from the same underlying posterior distribution. Notice again, as I go back to this, I have 3 chains here, but 2 parameters, right? Just to make sure we're on the same page. 3 chains, 3 workers doing the searching, but 2 parameters. So my posterior distribution is 3-dimensional here. So we're a little bit more complex here because we have 3 parameters. I'm pretending I have 3 workers doing the sampling, doing the searching, and my posterior distribution is 4-dimensional. So to do the diagnostic analysis, I'm going to use the CODA package. It's very common to perform this kind of work. And now what I'm going to do is combine all chains together. Combine all the samples from all the chains together using this list right here. And if I run the summary function, you can see that it produces the posterior mean, posterior standard deviation, various other, here are the quantiles. So we've done this already before using this quantile function up here. This being, you know, a R package that is specifically designed for convergence analysis. It produces a few more things, like it's easy to see what the middle 50% is, and it automatically produces the credible 95% confidence interval. But this tells us nothing about the convergence. And so to start to get at the convergence, the first thing we do is we use the trace plot. You guys have seen the trace plot. So here in a trace plot, you usually overlay the different chains together. And what you're looking for is called good mixing. So specifically, if I have one chain, now I have another chain, we really hope they found the same posterior distribution. We really hope that they are well mixed. So we hope that here is a stationary distribution as seen by the second chain, and here is the stationary distribution as seen by the first chain. So these are well mixed trace plots. So here I have 3 chains, right? I have the green chain, the red chain, and the black chain, and they are nice and stationary. In fact, they have a constant mean, and they cover the same sort of band of uncertainty as the iterations go from the first to the 5,000s. So this is a really good example of what a picture-perfect convergence analysis would look like. I know for a fact, because of how I sampled this, that these samples came from the posterior. They have, by definition, converged. When we're doing MCMC, we're not going to know they came from the posterior, and we're not going to know that they have already converged. So we'll be, for example, visually assessing the trace plot to determine if convergence and good mixing has occurred. So I hear you saying, well, that's very visual. It's very subjective. How do I know? The more quantitative method is what's called the Rhat, or the potential scale reduction factor. So this is what is called a Gelman-Rubin R-hat. It's a quantitative measure of convergence. Gelman-Rubin, and it's known as R-hat or potential scale reduction factor. Please don't make me write it out. I'm having problems with my stylus. So here's the definition. R-hat, and this is out of a 1992 paper, and I know that Andrew Gelman and company are working on an update. So I'll cite their old work that is still being widely used. Okay, so it's a ratio. It's a ratio of within sample variance and between sample variance. So W is within sample variance. I'm sorry, within chain variance. I'm so sorry. Within chain variance. B is between chain variance. And S is the number of samples from the posterior that we take. So let's take a look at the behavior. What happens as we take a large enough number of samples? So what happens as S goes to infinity? As the number of samples goes to infinity, this quantity right here goes to 1. As S goes to infinity, this entire quantity right here goes to 1. And as S goes to infinity, our hat goes to 1, which indicates convergence. So that's what we want. We want our hats, the potential scale reduction factors, of 1, because that is the case where in a way, my chains are covering the same space. And if they're covering the same space, I have found the same posterior from random starting locations using 3 separate sequences of random numbers. So that's what happens as we take a large enough number of samples. But the thing is, this is where mathematics meets reality, and we will never in our lifetimes observe the case where the number of samples goes to infinity. So the other case that happens a lot more frequently, because we can't possibly take an infinite number of samples, is if the between chain variance goes to 0. B is between chain variance, and for some reason I just can't write. But if we look at this plot, the between chain variance is the same as the within chain variance. They're literally overlaid over one another. So as the between chain variance goes to 0, and S is large, then our R hats go to 1. And that's again what we want. At convergence, our R hats are near 1. Now in older samplers, in older MCMC world, there would be rules of thumb like, well, you can stop sampling when your R hats are less than 1.1. then you read a different paper and they say, well, you can stop sampling when your R hats are less than 1.05. And then somebody else says 1.01. In the new world, it is relatively rare that it is anything besides 1.00. Yes, in theory, there are other digits here to consider, but in the new world, it is relatively easy to get our hats of almost exactly 1, which is what we want. When we look at what happens with our picture-perfect world, it's a picture-perfect world because that's how we set it up. I took samples from the posterior. I have baked in the fact that these are already converged. They're there. I have taken 5,000 samples at random from the same posterior. This is the picture-perfect case. I run this Gelman diag, which produces my R hats. These are my R hats. And they even give you the upper confidence interval here. I wouldn't pay too much attention to it because it assumes quite a few things to come up with it. But you can see all of the numbers are 1. So these chains have converged. In a paper, you almost always have some variation of this statement. Convergence was ascertained by a visual inspection of the MCMC chains, that's looking at the trace plot, and verifying that the R hats are 1 for all parameters. You will see that statement with some variation in almost all Bayesian papers, or at least you should. I can give you examples. Yes. I certainly try and put one in. So the trace plots indicate good mixing, convergence. Our Gelman-Rubin R hats, the potential scale reduction factors, are all 1. That indicates convergence. The next question is, okay, so you have converged. Whoops. But now, how uncorrelated are my successive samples? How many pieces of independent information am I getting from the posterior? So the concept is effective sample size. Effective sample size, or ESS. The thing is that usually MCMC samples are not uncorrelated. And to see that, the position here is correlated to where you were before. Using relatively simple MCMC techniques, your subsequent positions inside the posterior tend to be correlated. To what degree, that is the question. So usually, successive MCMC samples are correlated. As this correlation increases, the effective sample size, that is the number of independent pieces of information from the posterior, starts to go down to 1. So that is, of course, a silly edge case where if you take 1,000,000 samples that are almost perfectly correlated, that is the same. You've learned the same about your posterior as taking just 1 sample. So what we're looking for in our effective sample size, what we want is ESS, well, as large as possible, but ESS that is approximately equal to number of requested samples. Remember that I took 5,000 from each of my chains, and so I hope my effective sample size in my picture perfect case is near 15,000. I took 15,000. Let's look at what my effective sample size comes back as. 15,000. And it's actually a little bit higher for C. Why is it higher? How could it be higher than the number of samples that we actually requested? In the case of negative autocorrelation, the effective sample size may actually be bigger than the number of samples that you requested. And basically what this indicates is you're bouncing around between the tails of the distribution without sampling the middle as much. Now, is this a problem? I don't think so. And if you think about it, you can compute the mean and the median by having the tails. But you can't possibly find anything out about the tails if you only have samples from the middle. So it's not an issue if you're sampling the tails and if you're interested in that posterior median, for example. But this is also not that big of a deviation from the number of samples that we requested. Omega and our alpha, our shape parameter, are exactly at 15,000. So omega and alpha, this is an example of no trend, no pattern. This is white noise. These are completely uncorrelated successive samples. Why? Because I made it so. I took random samples from the posterior with replacement. So again, I'm looking at a picture perfect case that, quite honestly, we will never likely see again as we move into MCMC world. Usually, effective sample size is a little bit smaller, or you hope it's only a little bit smaller than the number of samples that you requested. If it's a lot smaller, then you have a problem. Then, your posterior distributions are not based on as many pieces of information as you might think. So something that is in the same idea, I have the autocorrelation function. ACF is the autocorrelation function that can look at, well, how correlated are successive samples. So this is sort of a classic autocorrelation function. So lag 0 means that the sample is perfectly correlated with itself. Okay, that's nobody cares about that. That's not big news. And then here, lag 1 means successive samples, the first and the second and the third and the fourth, on average, are correlated to this amount right here. This is essentially 0. So this agrees with our effective sample size in that successive samples are virtually uncorrelated or are uncorrelated. And now, usually what happens as we get farther apart, we're no longer looking at 2 adjacent samples. We're looking at samples that are 5 steps apart. Usually our autocorrelation decreases, and it still does, but all of these numbers are essentially 0. This agrees very nicely with effective sample size being large. This is how the autocorrelation function agrees with the effective sample size. The next thing, again, staying in a correlation world, we can look at how correlated are our 3 or however many parameters you have. So this is the correlation of Xi with itself, omega with itself, and shape with itself. This is basically the correlation matrix of all of our parameters. So this is where you're unlikely to see zeros, because if we go back to all the way in the beginning, where I listed the PDF, the probability density function of a skew normal, you can see, for example, inside right there, you have this alpha parameter is basically interacting directly with your other parameters without interacting with the data. So that is an example of when it will be hard to estimate alpha separately from Xi and estimate alpha separately from omega. So this is reflected in this cross-parameter correlation matrix where there are some non-trivial correlations between all three of our parameters. But we start to worry when these start to approach -1 and 1. If we were approaching -1 and 1, then we definitely could say we don't have enough information in our data to separately estimate 3 parameters. But here we have moderate correlations. I'm not surprised because alpha, as I just showed you, interacts with the 2 parameters here and here. So, and of course, in a ratio, C and omega interact as well, right? So it's not surprising that they share information. So here, you're looking for correlations that are approaching -1 and 1. And if that's the case, then you really have to rethink your model. You might be trying to estimate more than what you have than the information you have in your data. The plot is, I think, unnecessary. For a small enough number of parameters, it's actually less informative than the correlation matrix. And you can imagine if I had 50 parameters, then that plot would just get unreadable. Because how are you going to find the pairs that are highly correlated? To be honest, I don't look at this that much, but you will see some books and papers do. So I just wanted to put it out in front of you. So before we end this unit, it's always good to check our work. So as we go down, I wanted to check my work using a bona fide Bayesian analysis package called BRMS. In the next unit, we will begin using it. And there's a non-trivial installation process that we'll go through in the future. So I'm not going to spend too long on this, but just take a look that it has a very friendly, user-friendly formula interface. Like this is just like the formula of your Elmer function. We get to set our priors using just English language, right? So we set our intercept, which was our Xi parameter essentially. Sorry, it's the mean, not the Xi parameter, it's the mean. We set the prior for the mean, we set the prior for the standard deviation, and we set the prior for our alpha parameter. There is an estimation component, and then it produces this output. So based on what I told you in this lecture, you can already see here is the Rhat. Here is a little blurb about the Rhat and the ESS. And you can see what I requested was 4,000 samples for 3 chains. So what I requested was 12,000 total samples. What I got in my effective sample size is more like 5,000 to 6,000, which is still great. If you're getting 5,000 to 6,000 independent pieces of information about your parameter, you can build a nice distribution, take various percentiles, have a good sense of that 2.5 and 97.5 percentile, etc. But in this, using this Bayesian analysis, you can see that we went from 12,000 samples requested to about 5,000 to 6,000 effective pieces of information. My Rhats are all 1.00, so that means things have converged. Things have converged. And that makes me happy because that means that my posterior estimates mean something because I have converged to a stationary distribution that will take to be my posterior. As we compare, I look real good on the first 2. The first 2 are, within a few decimal points of one another, and as are the credible intervals, which is important. Alpha is a little bit farther off, but the difference is probably due to the fact that using this bona fide R package, what I'm setting my priors to are not the individual parameters. They're actually the mean and the standard deviation. So I'm setting the priors, my priors, for these terms right here, and not the individual parameters that make up these terms. So that is probably accounting for the difference, the tiny difference in the alpha, in the shape parameter. But the major finding that this is left skewed, and it is significantly left skewed in that 0 is nowhere to be found inside the 95% credible interval, still is supported. Okay. I know we're just starting a peek into the MCMC world. I wanted to introduce this because, as I keep repeating, this is the first time we will see a picture-perfect case. A picture-perfect case where we get perfect convergence. We get perfect-looking trace plots. We get Gelman-Rubin R-hats to be exactly equal to 1, and no autocorrelation whatsoever between successive samples. As we move on into kind of a real world, you can always rely back on this picture-perfect scenario to try and gauge if your real model, how close your real model came to convergence. Okay, guys, thanks for your attention. We're now done with Unit 2. Look out for the homework assignment being posted this week. It'll be due a little while from now. Next Tuesday, we have our second synchronous activity. We'll play around with some multi-parameter models. Thank you guys for your attention. Hope you're staying safe. I'll talk to you later.